I'm going to discuss axisymmetric finite element. So, okay, it is not writing. So, mm, hello, is my screen visible? Hello, is my screen visible? Okay, okay. So yeah, so last class I discussed the plane stress, plane strain, four-noded isoparametric finite element, and we also discussed know how to numerically integrate and get the element level stiffness matrix and load vector. So today I am going to talk about axisymmetric finite element formulation. So basically, when we say axisymmetric, so what we are saying is that the body of interest can be represented. Is a body of revolution about axis of symmetry. So there are two requirements here that when we talk of axisymmetric finite element, so one is that geometry and the other is loading. Both have to be axisymmetric. So geometry and loading both are axisymmetric. So the examples are like if, if you have a rod, let us say there is a rod. So there is an axis of revolution about which a cross section can be rotated and generated. So let us say that we have this as a rod. This is the rod, and this is under axial load. Let us say. And here although this can be modeled using truss element, but what we are saying that when we look at the this length to diameter ratio, so length to diameter ratio is very small, say L by D equal to 3 2 or 1, and in that case we want to model this. So for modeling this rod, because this is a body of revolution, that means the entire this cylindrical rod. Now this is a cylindrical rod. So this cylindrical rod can be generated by revolving this one cross section. Say this cross section about the axis of revolution. So that is the one example of axisymmetric problem. So we can, and the loading is also axisymmetric. That means it is independent. Throughout the circumference, the same loading is there. So this is one example. Another is if you take a thick cylinder. So let us say if this is the axis of revolution for the thick cylinder, and then the thick cylinder is like this, and let us say it is subjected to internal pressure. So the whole cylinder can be generated by revolving this cross section about this axis of revolution. So if we revolve now this cross section about the axis of revolution, we get the thick cylinder. So this is an example of thick cylinder under internal pressure. Thick cylinder, and this is axis of revolution. Axis of revolution or axis of symmetry. So this is one example. Now this kind of a problem you can solve using, rather than modeling this using three-dimensional elements, you model only one cross section. So the computational requirement is less. That means you will have lesser number of total degrees of freedom. So computationally it can be solved no efficiently. So that is one example. And general case would be again a body of revolution, a general body of revolution. So let us say we have a body of revolution like this, but it is thick. So this whole body again can be generated. No, this is the cross section, and this whole body can be generated. So the loading is, for example, no, the simplest example I can give is in the, of course, submarine. You will have some parts like this, and and many of the, let's say, conical cell, thick conical cell can be modeled using this. So this is again the axis of revolution or axis of symmetry, axis of revolution. So this is axis of revolution, and this is an example of body of revolution or cell of revolution. You can say body of revolution. So these are the examples where we can use the axisymmetric model. So rather than modeling the entire body, that is three-dimensional body, we are modeling only one cross section. So number of elements would be less and the number of degrees of freedom would be less. So in this model, what we are doing in all the cases, all the examples I gave, basically just we model the one section on one side of the axis of symmetry. So we model we model one cross section. Cross section means the one which can be revolve around the axis of revolution and can generate the entire body. So we model one cross section on one side of the axis of symmetry or axis of revolution. Axis of symmetry, the same thing. Axis of symmetry, or you also call it as axis of revolution. So you can generate the entire body by revolving the that cross section. So that is why we are using this. So no, these are the examples. So of course, if you look at most of the submarine would be basically the components would be thin cells, but some parts you will have which can be modeled. Of course, the this propulsion shaft can be modeled as a body of revolution under the of course torque, which is axisymmetric, and also the, of course, if the bending load is there, you cannot, obviously, in case of bending, the loading is not same along the thick no, the circumferential coordinate direction. So you cannot model under bending loading, but under the axial load and under the internal pressure load you can model that. So now and of course the thick cylinder, so that's the main example is thick cylinders are body of revolutions, that is what you can model using this. So wherever you have that kind of a body, it can be modeled using axis of this axisymmetric finite element. So we will discuss start with the basic concepts. So first, as we have been doing, first thing is we look at the displacements. So displacements are again, in the, we are assuming that the geometry is axisymmetric, so we can generate the entire geometry by rotating one cross section about the axis of revolution. The loading is independent of the circumferential coordinate theta. Every theta has got the same loading, so there would be only displacement along the radial direction. So if I take, let us say, if I take a cross section and the coordinates are x and y. X is along the radial direction and y is along the axial direction. So let us say this is the body under consideration. This is the body, and we want to look at the displacement at any point P with coordinates x and y. So the displacements would be u, which would be function of x and y. So this is basically radial displacement, and then you will have v along the y direction, that is along the axial direction, that will also be function of y. So this is the axial displacement. And the third is w would be 0, so that means we can say no circumferential displacement. The theta is a circumferential direction, no circumferential displacement. So yeah, these are the two independent displacements. So you would see that in terms of displacement, it is similar to plane stress, plane strain problems. There also we had two displacements u and v, which were functions of x and y. But in this case, of course, this is the body of revolution, and you would see the x coordinate is, of course, is the radius at any point p. So if you see over here, so this is your x coordinate, which is radius, and y is, of course, the y coordinate of any point, that is axial coordinate. So with these two displacements, if you look at the strains now, so more or less you would see that this is similar to plane stress, plane strain problems. So you will have now strain, only thing is compared to plane stress, plane strain, we will have one extra non-zero strain. So there would be three normal strains: epsilon xx, epsilon yy, epsilon zz, and gamma xy. So out of this, now if you look at epsilon zz, we can also say that epsilon theta theta, and this is epsilon xx, no, epsilon zz, which is equal to epsilon theta theta. We call it as circumferential or hoop strain. If you no, but we need to express these in terms of displacements, because displacements are our basic unknowns. So you would see epsilon xx is similar to plane stress, plane strain, it is del u by del x, and epsilon yy strain along the y direction is del v by del y. But the hoop strain, although there is no displacement along the z direction, but there is a hoop strain, and that hoop strain is divided, u display radial displacement divided by radius x. That is the hoop strain epsilon zz, and gamma xy will be equal to, of course, del u by del y plus del v by del x. So you would see that epsilon xx, epsilon yy, and gamma xy are similar to plane strain problem, but this is, the hoop strain is an additional strain component which you have in case of axisymmetric problems. So we will have to account for that strain as well over here. And as you know, the epsilon x-axis, if you take a line element parallel to x-axis, so change in length per unit to original length when the original length tends to 0. That is what is your epsilon x-axis. And similarly, epsilon y is, if you take a line element parallel to y-axis of length delta y and look at its change in length delta v, so then delta v upon delta y in the limit when delta y tends to 0 is epsilon yy. And similarly, this is a change in angle between line elements parallel to x and y. So that is gamma xy is change in angle between line elements parallel to x and y. And epsilon zz, how do we get non-zero epsilon zz? So it is like this, that if you take a circle, so say originally the circle is of radius x, in the body, and then under the application of loading, so this circle deforms and takes a deformed shape like this. So because we have a radial displacement u, so then the final radius is x plus u. So you would see that this is the deformed circle, and this is the undeformed circle. So this is undeformed circle. So actually, if you look at the epsilon zz, the interpretation I wanted to give you. So this is change in circumference per unit original circumference. So change in circumference would be circumference in the deformed configuration minus circumference in the undeformed configuration. So circumference in the deformed configuration would be 2 pi, radius is u plus x, and circumference in the undeformed configuration is 2 pi x, and divided by the original circumference, that is 2 pi x. So you will see that this comes out as u by x. So this is what you have as the hoop strain or the circumferential strain for these problems. And corresponding to these strains, you will have the corresponding stresses. So if you look at the stresses, what are the non-zero components of stresses? And of course, you would see that here I am not discussing how to find out the principal stresses, how to find out the Wien Mises stress, how to find out the maximum shear stress, because they are the ones which would be used in the design for these multi-axial loading problems. So that I think you should be able to refer to any book on basics of solid mechanics. Either you would have studied, so you should be able to do that for practical applications. So the sigma will have non-zero, again four components, three normal stresses, sigma xx, sigma yy, sigma zz. These are three normal stresses along xy and z direction, and there is a shear stress tau xy. So these are the non-zero components of stresses, and the tau yz, and tau zx, these would be equal to zero. So that is tau yz and tau zx. These two shear stress are zero, and the four stress components are non-zero. And as usual, the way we did for the plane stress, plane strain problem, we need to relate the stresses with the strains. So we have what is known as the constitutive relation. That is the relationship between stress and strain. So again, no, for I am writing only for linear elastic isotropic material, although you can also talk about the orthotropic materials and so on. So linear elastic isotropic material. So for this, of course, no, the form of the stress strain relationship is going to be same the way we had for the plane stress plane strain problem. So C is a constitutive matrix into epsilon, and no, where if you look at C, no, so sigma we have already defined, epsilon we have already defined. So here for the axisymmetric problems, C is similar to what we had for the plane strain case. Only thing is one normal strain and corresponding normal stress are the extra non-zero components. So we have E upon 1 plus nu and 1 minus 2 nu. So you can of course easily write the strains in terms of stresses and then invert that relationship, so you get this. So I am directly writing that the relationship, no, the basically stresses in terms of strains. So here you have 1 minus nu and nu 0, three non-zero normal stresses in strains, and then no, the one shear stress, and then you have nu 1 minus nu 0 0, and then 0 0 0 1 minus 2 nu by 2. So this 1 minus 2 nu by 2 is such that we get ultimately the last term as E upon 2 into 1 plus nu, which is G. So basically sigma xx, you would see that no, you this is C, so you should be able to write sigma xx, sigma yy, sigma zz, and tau xy in terms of stresses. Now if you next is for the development of the eliminable governing equations, although one way is that we look at the differential equations and then basically we obtain the weighted residual statement and then weak form and the integral functional, or we can write directly the integral function also. Let me write the total potential energy functional. So total potential energy functional I would be strain energy. So strain energy is half integration over volume, and then you have sigma transpose into epsilon, and sigma is C into epsilon. So sigma transpose becomes epsilon transpose into C transpose. C is symmetric, so its transpose is same as C. So you can write this as epsilon transpose into C into epsilon into dV. This is the strain energy. The first term is strain energy, then potential of body forces. So this we are writing similar to what we have been doing earlier. So UV transpose into body forces, and we will have only two components of body forces along x and y direction. So we will have FBx and FBy, and then integration over volume, and then we will have of course the integration over the boundary of the element. So it could be the boundary could either be having normal along radial direction, or it can have normal along the axial direction, that is y direction. So I'm writing as a boundary integral, and again this is similar to the terms are similar to the plane stress plane strain problem. So same quantities we are using, the body forces fbx fby, traction forces tnx tny, they are also the forces per unit area. And then of course here we get the, we need to multiply 2 pi x into ds, where ds is the length along the boundary. So either the boundary is having normal parallel to x axis, that is radial direction, or boundary having normal parallel to y axis, that is axial direction. So this is the total potential energy functional. So this is as far as the basics of any axisymmetric problem formulations are concerned. Now we look at a particular element. So let us say, no, we want to look at the element, and again we want to do the axisymmetric formulation. So let us say we have an element, this x is a radial direction here, y is the axial direction, and the element is a let us say again four noded quadrilateral. So having 1 2 3, these are the four nodes, and the coordinates also will have. And then in this we are mapping it to basically square in the natural coordinate space, xi and eta, and the nodes are 1 2 3 and 4. So we are talking about four noded element. So this is the element we are talking about, which is four noded isoparametric axisymmetric finite element. Isoparametric, that means geometry and the displacements are going to be interpolated using same shape functions. So four noded isoparametric axisymmetric finite element. So the shape functions are going to be same what we developed for the plane stress, plane strain. So I'm directly writing no u and v. When you look at the displacement approximation, so it would be similar to what we had for the plane stress, plane strain problems. Actually, if you look at many of the packages, no, we'll have this 2D element, and then you can choose either plane stress, plane strain, or axisymmetric, because the formulation is more or less the same for all the three problems. So these subroutines for these are in the softwares are actually combined. So if you look at the degrees of freedom, so first we write all the degrees of freedom of first node, second node, third node, and then fourth node. Primary variables are displacements along x and y, that is radial and these axial displacements. So for the element total we will have 8 degrees of freedom. So u1e, b1e, u2e, b2e, U3E, V3E, U4E, and V4E. So these are the values of U and V at node 1, 2, 3, and 4. And the shape functions are no that same N1, N2, N3. I'm not writing them again because we have already defined them for the plane stress, plane strain case. So the same shape functions are used here. So n1 0, n2 0, n3 0, and n4 0, and then v is 0, n1. So this is giving you u equal to n1 u1e plus n2 u2e plus n3 u3e plus n4 u4e, and similarly for v. So as usual, we write no this matrix as H matrix into DE. So this is H and this is D, and you interpolate basically no x and y also in a similar exactly the same way. X is of course the radial coordinate or its radius. So this you will write I equal to 1 to 4 ni into xi, and similarly y coordinate you will write as ni into yi. So sum of four terms basically, I going from 1 to 4. And the Jacobian matrix will also be same the way I had introduced the concept of Jacobian matrix. So once you have J expressed in terms of xi and eta, no x and y expressed in terms of xi and eta, you can get your J, the Jacobian matrix, which is del x by del xi, del y by del xi, del x by del eta, and del y by del eta. So this is a Jacobian matrix. And then of course no you need basically the strain interpolation for the strain, so epsilon, and which is consisting of for axisymmetric problems four elements, three normal strains epsilon xy, epsilon xx yy zz, and the gamma xy. Gamma xy can also be written as twice of epsilon xy for epsilon xy is tensorial component of strain. So this will be, again this will be written in terms of the derivatives of the shape functions. So we already have learned how to get the, once we know the shape function in terms of xi and eta, then how do we get their derivatives with respect to x and y. So we have already discussed that concept. These degrees of freedom are same: u1e, v1e, u2e, v2e, u3e, v3e, u4e, and v4e. So these are the same degrees of freedom. Now epsilon xx is del u by del x. So it is coming in terms of u, and it's the derivative with respect to x. u1, u2, u3, u4 are basically values of u at node points, so they are constant. So the derivative will only go with the shape function. So here you will have del n1 by del x 0, del n2 by del x 0, del n3 by del x 0, and del n4 by del x and 0. Then epsilon yy is del v by del y, so that would be 0, del n1 by del y 0, del n2 by del y 0, del n3 by del y 0, and del n4 by del y. So that is epsilon yy. And epsilon zz we have seen is basically u by x. So it would be u means n no, will be going with u1, u2, u3, u4. So we will have here n1 by x 0, n2 by x 0, n3 by x 0, and n4 by x 0, so that it is in terms of u. And then the shear strain gamma xy is del u by del y plus del v by del x. So del n1 by del y plus del v by del n1 by del sorry um, no, here with u we will have del n1 by del y, and with v we will have del n1 by del x, and then we will have del n2 by del y, del n2 by del x, del n3 by del y, del n3 by del x. So they u derivative is with respect to y, and v derivative is with respect to x. So del n4 by del y and del n4 by del x. So yeah, these are the strain components. So now we, as usual, we denote this as strain displacement matrix into vector of elemental degrees of freedom. So this is B and this is D. Now you will see B here is 4 by 8 and D is 8 by 1. And of course, if you look at the H matrix over here, so H matrix is 2 by 8 and D is 8 by 1. So once you have defined H and B, the procedure for developing the element level governing equations is the same. That is, we basically substitute these approximations in the integral functional, then take the variation of the integral functional and equate it to 0, and then that is delta I equal to 0 for arbitrary value of delta D, and from there we get the element level governing equations. So those will be same. So let me write. You will see that form of the the element level governing equations is actually going to be same. So you should be able to derive. I am not deriving that, so I am directly writing element level governing. So I'm just telling you the essential aspects of axisymmetric finite element where you can use this. So in this case, the governing equation for is the same. That is element level stiffness matrix is equal to f external, and the assembly imposition of boundary condition and solution is also same. So I won't be discussing those aspects. So what is different, that is what I am discussing here. So where if you look at the element level stiffness matrix Ke, so it would be now the volume integral is converted into integration with respect to xi and eta. So basically integration from -1 to +1, -1 to +1, B transpose into C into B, and then we will have the volume would be, so when this is the axis, and let us say this is the body any you are considering. So what we are doing is to get the volume dv, we are taking a differential element over here, this differential element which is written as j times d xi d eta, and into circumference, that gives you the volume. So that means if you revolve this area, small area, know about this axis of revolution, you get the volume. So for that, you multiply the length of that circle, which is 2 pi x. So you will have here 2 pi x into determinant of j into d high d eta. So this will be basically the stiffness matrix, and this can be, again, we will not be evaluating it explicitly by multiplying and integrating each element with respect to xi and eta, but we do the numerical integration. So that is, we write it as summation I going from 1 to m and j going from 1 to n, as we did earlier. So we have here b transpose into c into b into 2 pi x. Of course, x is also a function of xi and eta, as you would know, because x we have expressed already in terms of xi and eta. This is evaluated xi I eta z into wi wj. And similarly, know the f external for the element is integration -1 to +1 -1 to +1, and then we have h transpose, then body force components fbx and fby, body forces along x and y, and then 2 pi x to get the volume into determinant j d is high d eta. So this is the external load vector, which is only difference compared to the plane stress plane strain problem is basically presence of this term, no, which gives you the ultimately volume. And this again can be written as using Gauss quadrature numerical integration. I can write this as I equal to 1 to m dash and j equal to 1 to n dash, and then we have no here h transpose fbx fby and 2 pi x into determinant of j, this whole thing evaluated at xi I eta j wi wj. And of course, then you have this internal load vector. That internal load vector I am leaving as it as the boundary integral in the form of boundary integral. So this is integration over the boundary, and again you have basically no h transpose, and then the tractions, boundary forces per unit area tnx tny, and then you need to multiply by 2 pi x into ds, where s is the bound no length along the boundary. And here if you look at the values of m and n, that m dash and n dash, so they would be similar. So because we are talking of four noded axisymmetric element, so in n you have highest power of xi or eta as 1. So when we do b transpose b, we will get highest power of xi eta as 2 for the rectangular element in the physical coordinate space. So we will have of course one x also. So you will see the highest power of xi and eta in b transpose c into b into x. This x is also there. X is in terms of n1 n2, so it's also of highest power of xi or eta is 1. So you will see that the highest power of xi or eta is basically 3. So no n is equal to m is equal to highest power of xi and eta is 3. So it would be 3 plus 1 by 2. So this will be 2. So you would see that n and m and n are going to be actually 2. So still it would be a 2 by 2 integration for the axisymmetric element. That means we will have no, when we talk of element in the natural coordinate space, xi and eta will have 4 integration points that we have discussed already. So this is integration point 1, this is 2, this is 3, and this is 4. So we evaluate this whole thing at these 4 points, multiply by the weight functions, and add all of them together. So this is, and so similarly if you look at of course n dash and m dash, so they will also, because the highest h is having highest power of xi eta as 1, and then x is having highest power of xi eta as another 1. So 1 plus 1 2. So 2 plus 1 by 2 approximated to next integer. So we will again find that n dash is equal to m dash is equal to 2 plus 1 by 2 approximated to next integer. So that will also be 2. So it would be basically a 2 by 2 integration for both the stiffness matrix as well as the load vector. So now the in the library, when you look at the library of these packages, finite element packages, so you have 1D elements like truss element, beam element, frame element. Then you have plane stress, plane strain, axisymmetric elements, and then you have basically plate bending elements. So that I want to take at the end, but Now next is the 3D solid element. So now why do we go for 3D solid elements is whenever all the three dimensions of the body are comparable and we cannot make any approximation, that is all the displacements, all the stresses are non-zero and they are functions of all the three coordinates x, y and z, then we go for the 3D solid elements. So that is the next I'm going to discuss. And no, if you have any question in between, any doubt, you please ask or you can write in the chat box. So I know you should not basically keep any doubt pending. So with this, now when we discuss the 3D solid elements, so you have basically the information about different types of finite elements we use any in any analysis. So you will be able to make a deformed, informed decision that what element to use. And as I said, that you go by the whatever assumptions are made. So if those assumptions, depending on the, of course, for any problem you can always use the 3D solid elements because in that there are no assumptions made as far as the variation of the displacements, stresses, and strains along the three orthogonal coordinate directions are concerned. But then you would end up using large number of elements, so computationally it becomes very time consuming, and that is why you try to exploit the use of other elements which are computationally less involved. Will end up into lesser number of elements and lesser number of degrees of freedom. So the next I'm going to discuss this 3D solid element, and I'm mainly going to discuss basically the 3D solid element. So I'm going to discuss 8-noded isoparametric brick element. Of course, in 2D you could have 8-noded elements also. So only difference would be that you would have 8 nodes and the shape functions would be of course different. The rest of the sizes of the matrices and vectors would be different. Otherwise, everything is same. So maybe I would demonstrate sometimes the other elements. So now first let me talk of this 8-noded isoparametric brick element. So commonly we call it as a brick element because it is the shape is similar to brick. So that is why no, this common terminology is that it is referred to as a brick element. So here what again we are talking of is isoparametric element. So that means the actual body be discretized. As I said here, there are no all the dimensions are significant and no, you have all the displacements along xyz are non-zero and functions of all the three coordinates xyz. So that is why you use the 3D elements. So now let me sketch the element. So you have these coordinate directions, say x, y, and z, and the element is a parallelopiped over here. So this is the basically like a brick you see, and the node numbering is, so we number this corner node as 1, 2, 3. The bottom nodes I'm numbering first, and then again I'm starting here 5, 6, 7, and 8. So in 2D also we have 8-noded element, but that is in the same plane, in the xy plane. But here this is in the 3D space. So this is the parallelopiped. This is parallelopiped in the physical coordinate space. And again this is mapped to a cube in the basically natural coordinate space. So in the natural coordinate space you have this element. So although what I have drawn here is more looks like a parallel cuboid, no, actually cube, but no, this can be any parallel pipe. So it is not necessary that no angle between these edges have to be 90 degrees. But in the natural coordinate, of course, it has to be a cube. So now the coordinate directions are, now you come from here to here. So from the center, now you have xi coordinate, and then from here you have eta coordinate, and then from here you have now another third coordinate, zeta. So now we have xi, eta, and zeta. So these are the coordinates. Nodes are same, 1, 2, 3. So 1, 2, 3, 4, 5, 6, 7, 8 in the physical coordinate space are mapped to 1, 2, 3, 4, 5, 6, 7, 8 in the natural coordinate space. 3, 4, and then we have 5, 6, 7, and 8. So now this is the element we are talking about, and this is cube here. This is cube. If you look at the nodal coordinates, in the physical coordinate space, the nodal coordinates are going to be, like node 1 will have coordinates x1, y1, z1. Node 2 will have x2, y2, and z2, and so on. No? Node 3 will have x3, y3, z3, and so on, etc. Similarly, for the the natural coordinate space, node 1 will have coordinates as you see. The origin of this xi eta zeta coordinate system is at the center. So coordinates of this nodes are node 1 are going to be, all the xi eta coordinates would be negative. So -1, and then node 2 xi coordinate would be positive. So 1, -1, -1. Node 3 xi and eta coordinates would be positive. So 1, 1, -1. And node 4 xi coordinate is -1, eta coordinate is +1, and zeta is -1. So these are the coordinates. So similarly, if you look at the node 5, we'll have -1, -1, and +1. 6 will have 1, -1, and +1. And 7 coordinates would be 1, 1, and 1. And then the coordinate of node 8 in the natural coordinate space would be basically uh, -1, 1. So that is, no, you can look at based on the coordinate system, -1, 1, and 1. So these are the natural coordinates of all the 8 nodes of this element. Now in any formulation, as we are starting, so the first thing we are talking about is the displacements. So if you look at the displacements, we have, as I said, no, the displacement along all the three directions are non-zero. So we will have u, which is a function of all the three coordinates x, y, z. U is the displacement along x, v is the displacement along y, function of x, y, and z. W is the displacement along z, which is also function of x, y, and z. So we will have no all the displacements as non-zero for the 3D solid body. And then if you look at the strains, so there are now 6 components of strains. 3 normal strains, epsilon xx, normal strain along x direction, epsilon yy, normal strain along y direction, epsilon zz, normal strain along z direction, and then you have shear strains, gamma xy, gamma yz, and gamma zx. So these are the non-zero components of strains, and we need to worry about the strain displacement relations. So epsilon xx is rate of change of u with respect to x. So del u by del x. Epsilon yy is rate of change of v with respect to y, del v by del y. And epsilon zz is del w by del z, rate of change of w with respect to z. And then the shear strains are similarly, no, these are the standard relations. No, we have strain displacement relations. Those have to be used over here. So you have gamma xy is equal to del u by del y plus del v by del x, and gamma yz would be equal to del v by del z plus del w by del y, and gamma zx would be del u by del z plus del w by del x. So these are the various strain components for this, for the 3D solid body. And then of course we have the stress strain relationship. So the the stresses, if you look at, there are again 6 components of stresses which are non-zero in this. So if you look at sigma, sigma would have 6 components: normal strain along x, normal strain along y, normal stress along x, normal stress along y, normal stress along z, shear stress tau xy, shear stress tau yz, shear stress tau zx. So these are the non-zero components of actually stresses for the 3D body, where no sigma xx is normal stress along x, y, and z similarly, and shear stress is the shear stress in xy plane, in yz tau yz is shear stress in yz plane, and tau zx is shear stress in zx plane. Then we need to look at the stress strain relationship. So next is what we call as constitutive relation, that is relationship between stress and strain. Again I am going to write this only for the linear elastic isotropic material. So the form of the relationship is same what we discussed, say for example for the axisymmetric case. So C into epsilon, where C is the constitutive matrix, and this C matrix is given as, for this constitutive matrix C is given by, the form is same, only thing is that all the stresses and strains are non-zero. So we have 1 plus nu, 1 minus 2 nu, and now it is going to be a 6 by 6 matrix, because now we have 6 components of stresses and strains. So this is 1 minus nu 0 0 0, and then nu 1 minus nu 0 0 0. So for isotropic materials there is no coupling between the normal strains and shear stresses, and similarly between the shear stresses and the normal strains. So that is why those coupling terms are zero. Only there is a coupling between the normal stresses and normal strains. So 1 minus nu 0 0, and similarly there is no coupling between the stresses and strains in different planes. So here you have 1 minus 2 nu by 2, so that you get, when you multiply this with the 1 minus 2 nu by 2, you get E upon 2 into 1 plus nu, which is G. So 0 0 0, 1 minus 2 nu by 2, 0, and then 0 0 0 0, 1 minus 2 nu by 2. So this is the constitutive matrix for the 3D. So you would see that the formulation is actually same. Only thing is now the similar to axisymmetric problems. Only thing is that no, the more number of non-zero components of displacements, strains, and stresses are there. So that's the only difference. So now for this problem, if you look at the total potential energy, functional, again it would be consisting of basically the stresses and the strain energy and the potential of body forces and potential of surface tractions. So this I would be, you would see, can be written as half an integration over volume of the body, and then the strain energy is half of sigma transpose into volume. So that is sigma xx into epsilon xx plus sigma yy into epsilon yy plus sigma zz into epsilon zz plus tau xy into gamma xy plus tau yz into gamma xz plus no, and so on. So those 6 components all put together can be written as sigma transpose into epsilon, and sigma is C into epsilon. So you can ultimately write that as epsilon transpose into C transpose is equal to C, because C is a symmetric matrix, and into epsilon, and then you have volume integral dV, that's the volume integral. Then you have body forces. Now the body forces would be there in all the 3 directions. So you will have UV transpose, and then FBX, FBY, FBZ, body force along XYZ direction into dV, and then the boundary is now going to be surfaces. See, for the 1D problems, the boundaries were points. For 2D problems, plane stress, plane strain, axisymmetric, the boundaries were lines or curves. And for the 3D problems, the boundaries are going to be actually surfaces. So the boundary integral would be a surface integral, and you will have UVW transpose into TNX, TNY, and TNZ into DS, where DS is now the A surface area. So this is surface area, because boundary, now if you look at the elements over here, the boundaries are surfaces. Now if you look at the here boundaries, so these are the boundaries, they are surfaces. So the boundary integral now has to be a surface integral, and the body forces FBX, FBY, and FBZ are the forces per unit volume along X, Y, and Z direction acting throughout the volume of the body, and the surface tractions TNX, TNY, TNZ are the force, the forces per unit area on surface having normal along n, and the components of these force per unit areas are Tnx, Tny and Tnz. So these are the traction components. Traction components. So what we are saying is that suppose no, if you have this as the surface and outward normal is, this is the outward normal. So on this you will have a force along the normal direction. Let us say normal is not along any one of the, is not along the coordinate direction. So let us say we have one coordinate direction which is in this direction, so that would be Tnx. Another coordinate direction is this Tny, and this is Tnz. So these are the force per unit areas. Tnx is no force on a area having normal along n, component along x, component along y, and component along z. So these are the traction forces. And then now if you look at the interpolation, so now we'll have to look at the interpolation of all the variables. So we will have so if you look at the interpolation is similar. So now there are 8 nodes. So you will kind of know, if you look at the, I will write in terms of directly in terms of shape functions, but what essentially we are doing, that we are writing say u, and similarly v, w, x, y and z in a identical manner. So it's like a0 plus a1 chi plus a2 eta plus a3 zeta. So and then you have plus now a4 xi eta plus a5. So now these combinations will have xi eta, and then we will have eta zeta, and plus we will have a6 into xi zeta, and then you will have so a4 a5, so a0 a1 a2 a3 a4 a5 a6, and then we will have a7 which would be xi, eta and zeta. So these are the 8 terms you will have in the approximate solution from the Pascal's triangle for 3D, that is with 3 coordinates xi, eta and zeta. So this is zeta. So now ultimately you can express this a0, a1, a2, a3, a4, a5, a6, a7 in terms of values of u at node points, that is u1, u2, u3, u4, u5 and u6, u7 and u8. So ultimately you would be able to write u is equal to I going from 1 to 8 ni into uie. Similarly you would be able to write v, the displacement along y direction, summation I going from 1 to 8 ni into VIE, and W, the displacement along z direction, again I going from 1 to 8 ni WIE. Same with the XYZ coordinates, because we also need to express XYZ in terms of xi and eta. So we write x is equal to ni xi, y in the summation is same 1 to 8, y is ni yi, and similarly z coordinate is summation ni zi. So this is how you will be able to write basically all the interpolations, and you would see the rest of the derivation is actually exactly similar to what we have been doing so far for the plane stress, plane strain and axisymmetric finite elements. So let me write the shape functions of ni's. So if you look at the shape functions are interpolation functions. So these are going to be now 8. So if you look at, let me sketch the element in the natural coordinate space again, so that I can refer to. So the now this is this side, this is xi coordinate, this is eta coordinate, and this is zeta coordinates, and the nodes are 1 2 3 4, then 5 6 7 and 8. So n1 is the shape function corresponding to node 1. So what we do is we take the equations of the surfaces excluding node 1. So then we will have to take this surface whose equation is 1 minus xi equal to 0, this surface whose equation is 1 minus eta equal to 0, and this surface whose equation is 1 minus zeta equal to 0. So we take the multiplication of all three. So 1 minus xi, 1 minus theta, 1 minus zeta. And then we'll have to make sure that this is unity at node 1. The coordinates of node 1 are minus 1, minus 1, minus 1. So we put here xi equal to minus 1, eta equal to minus 1, zeta equal to minus 1, we get 8. So we divide it by 8 so that this is unity at node number 1. So the shape function n1 is 1 by 8, 1 minus xi, 1 minus theta, 1 minus zeta. And then similarly n2, so this is corresponding to this shape surface, no, this particular node. So then you take this surface and this backside surface. So basically we'll have 1 by 8 and then 1 plus xi, 1 minus theta, 1 minus zeta. And this will ensure that n2 is unity at node 2 and 0 at all other nodes. Similarly n1 is unity at node 1 and 0 at all other nodes. So like that you would be able to write similarly n3 would be 1 by 8, 1 plus xi, 1 plus eta and 1 minus zeta. That continues to remain 1 minus zeta for all the nodes 1, 2, 3 and 4. And then n4 would be similarly 1 by 8, 1 minus xi, 1 minus xi, 1 plus eta and 1 minus zeta. Then n5 would be the top node, so you can write actually from the n1, n2, n3. Only thing is now in place of for node 5, 6, 7 and 8, in place of the top surface we will have bottom surface. The equation of the bottom surface is basically zeta is equal to minus 1 or 1 plus zeta equal to 0. So we will have in place of this term we will have plus here and the other things would remain same. So this would be 1 by 8, 1 minus xi, 1 minus theta, 1 plus zeta. And n6 would be 1 by 8 and then 1 plus xi, 1 minus theta, 1 plus zeta. And n7 would be 1 by 8, 1 plus xi, 1 plus theta, 1 plus zeta. And n8 would be 1 by 8 and then 1 minus xi, 1 plus eta and 1 plus zeta. So these are the shape functions. So today that is where I want to stop and now you please go through this. I will be completing this formulation of 8 noded this 3D element. So we'll have to next is we write the interpolation for UVW in terms of H and D. So we need to define H, we need to define B, and then we need to write the element level governing equation and involving B, H, and constitutive matrix C, Jacobian matrix, its inverse, and all those things. And then with that, we will be completing this in the next class. So I want to stop here. If you have meantime any question, you can ask. Anybody, any question? So I want to stop here today. Any question? Okay, then I am stopping. Thank you all for your attention.